Hi, NA Physics, it's Mr. Neff. Let's talk about plane mirrors. Before we do, did you hear about the man who sued the airline because they lost his luggage? I'll tell you about him at the end of the video. Or talk about mirrors, whether they're flat like today's video or whether they're curved mirrors like a video for a different day, is going to center around the idea that light travels in straight lines. Now, this is something that you learned whenever you were a little baby. You were in your crib and you reached for something and you found out that, hey, it is where it looks like it is. And so light from that thing entered your eye along a line, and all you had to do was move your hand backwards along that line and you found that thing. So you know deep down in your bones that light travels in a straight line. And so if you see a rabbit, where is the rabbit? Well, it's right there where it looks like it is. And that's true most of the time. But occasionally it's not true. And when it's not true is really the focus of these talks. So sometimes like this, where there's a mirror around the bunny, it's not, the light traveling in a straight line is not true. So that light is going to come off of the rabbit and it's going to hit the mirror, and some of it is going to get into your eye. Now you, deep down, you know that light travels in a straight line. And so what do? You put an image of a bunny where there really isn't one, because you're trying to make sense of, well, why is the image of a bunny coming in along this line? That must mean there is one there. Now you got a conscious brain that says there's not really a bunny there. You don't try to chase that one in the mirror. But some part of your brain says, well, there's an image of a bunny coming from there, so there must be one there. So it's that deep-seated assumption about light that makes us see these virtual images like this virtual bunny. A couple neat pictures. You can see here's a kid who they're learning about light for the first time or for the first few times, and they see a baby's face in this mirror, and they're reaching behind the mirror to find that baby. Now they're going to learn as they grow up that that's a virtual image and that's not the real thing. But for now, they don't understand that part. Their brain has put an image there, and they want to try to reach out and see that. And the same thing with a parakeet. Now, a parakeet is a social bird, and it would like to have a friend. But if you don't want to have two parakeets, you can have a parakeet in a mirror, and that parakeet will look at its reflection in the mirror, and it'll be perfectly happy. That parakeet will actually look into that mirror and even look behind the mirror like this kid is, and it'll think that it's playing a game of hide and seek with a friend, and it will be very, very much amused. And so you might say, well, I'm much smarter than a parakeet or a little baby. And yes, you are on one level, but there's also that part of your subconscious that is like a parakeet, is like a little baby, that says that light travels in a straight line and that image is coming along that line, so there must be something there. And I can tell you it's there because I can tell you think that because you see that image the same way that I do. Now we're going to talk about flat mirrors, that is plane mirrors. And we're going to say that the light coming off the mirror appears to be coming from a spot behind the mirror. It appears to be. No light is actually coming through there. The mirror is opaque, as something light cannot travel through the mirror. So because you know that light travels in a straight line, you put an image back there where there really isn't one. We're going to call those images virtual images. Images inserted by your brain into spots where the light seems to come from if it really did travel in straight lines. Sometimes those are called mirages too. Here I have an image of a person. Here's a real person, and they're standing in front of a wall of mirror, and they see their image in the mirror. Now, we call it a virtual image because, number one, it's coming from behind the mirror. Number two, it's coming from a place where light's not actually originating. There's no real light crossing there to give us this image. You might say, well, if it's a mirror, isn't it always going to be a virtual image? Well, no. If you watch my curved mirrors video, you will see no, that's not actually the case. So notice that even though the mirror is very long, the light from his foot is traveling up here, and if you watched our law of reflection video, you see that we have the angle of incidence and the angle of reflection. You can't see them perfectly here yet. Let me make a normal line in here for you, something like that. And so here's my angle of incidence and here's my angle of reflection, and those are the same, and that will hit the guy in the eye. Same thing from the top of his hair. This blue ray is coming over and coming back. Now I won't draw that normal line in there because the angles are really small, but you can still see that the angle of incidence and the angle of reflection are the same. Notice something, that even though he's a regular sized person, he actually only needs a mirror this big to see his whole body. And that's always a neat thing to notice, that the mirror only has to be half as big as the object that it's reflecting to show that whole object. So now, how do those distances compare? Let's do a little bit of vocabulary here. You saw them in the last picture, and now you'll see them again. We call the distance from the mirror to the object itself. And so in this case, this is going to be from the mirror over to the object itself. We call that the DO, the object distance. We call the distance from the mirror to the image, we call that the DI, the image distance. And then we say that the height of the object, HO, is from the principal axis. That's going to be the line that the base of the object is sitting on. You're going to see that over and over again as we talk about mirrors and lenses. From the base of the object that is the principal axis up to the top of the object, we're going to call that HO for height of object. And the same thing for the image, we're going to go from that principal axis up to the top, and we're going to call that H over HI. Now, if you notice something here, if you remember your geometry, you look at this triangle, this PAQ triangle, and this P prime Q triangle. So these two triangles right here. And I can show that those two things are congruent because they have the same angle right here. That's not the angle of reflection, but it's the complement to the angle of reflection. And then this side right here is all the same. It's shared from both. And then these are right angles right here. And so by angle side angle, I can show that those two are the same. And so all of that is to say that because of that, this DO and this DI, while they are the same size, they are congruent. And we could do something similar there. We could draw a line from P down here to B, missed it a little, and from P prime down here to B. And we could do a real similar thing and show that those two triangles are congruent too. And so then the HO and the HI are also the same size. Now, if you notice something, I didn't just say that DO and DI were equal to each other. I said they're the same size, and that's not quite the same thing. So with mirrors, we're going to have some signs that are really going to guide us in terms of math and then in conclusions that the math will give us. And so for the signs on the mirrors, we're going to say that the horizontal distances, the D's, they're going to start at the mirror surface. And if you go towards the observer, that's going to be a positive distance. And if you go away from the observer back into the mirror, you're going to call that a negative distance. And so this is similar to what you remember from math class, the Cartesian plane that we've used all along, similar to that, but it's just kind of using this spot where the principal axis and the mirror intersect each other. This spot right here, we call that the vertex. That's sort of like the origin here. Now, because most of the time the observer is drawn on the left of a picture, most of the time distances to the left are the positives. Do they have to be? No. It's just whatever direction is towards the observer is going to be the positive distance. And then away from the observer is going to be the negative distance. If you look at the vertical heights, you see something similar. Starting at the principal axis always, if you measure up, if you're going to an object that's above the principal axis, yeah, it's going to be a positive, and if it's below, it would be a negative. And so when you look here on this picture, I put spot 1, spot 2, spot 3, spot 4. You can see that spot 1 is a positive distance and a positive height. Spot 2 is a negative distance and a positive height. You can see that spot 3 is a negative height but a positive distance, and spot 4 is a negative distance and a negative height. So again, this reminds you a lot of points on a Cartesian plane, but it's not that left is negative and right is positive. It's towards the observer is positive and away from the observer is negative in terms of left and right. So all that is to say for plane mirrors then that the DO and DI, they're the same size, but they're opposites of each other because the DO is measured towards the observer and the DI is measured away from the observer. And the HO and the HI, that's the object height and the image height, they're the same thing. Later on, we're going to say that that ratio of that image height to the object height is called the magnification, and in this case, we're going to say that magnification is equal to 1. They are the same size and they're pointed the same way too. Just one quick example before we leave this idea. Here we say that we're seeing an object and it says that the observer from this point looks into the mirror, and where does the observer see the image? Well, the light that reflects off of the mirror from the object eventually to hit the observer, that has to obey the law of reflection. And so we're going to say that that light is going to travel along here something like this and hit the observer. You might say, how did you know to draw it there and not draw here, not draw there? Well, I looked at this problem before I started the video, and I knew that I needed something so that the angle of incidence and the angle of reflection had to be the same. And so they did us a favor and they put that point B on there. Now, the observer thinks that this incoming light travels in a straight line. And so it seems like this light's coming from the spot back here. Notice something. The real light I drew with a solid line. So the actual light, that's always a solid line. That's the convention you'll see all over the world. And then the imagination lines, the apparent path of a light, that's drawn with a dotted line. So my imagination, that's a dotted line. And so you can see that the light is coming from a spot, seems to be coming from a spot along this line. And now we know that since the DO and the DI are the same sides, it's just one is positive and one is negative. Well, here is my DO and here is my DI, and the DO was 4, 1, 2, 3, 4 units, and so the DI is 1, 2, 3, 4 units, just the other side of the mirror, and so spot A is it. Hey, before we leave, did you hear about that man who sued the airline for losing his luggage? Unfortunately, he lost his case.